I'm Thomas. I am currently teaching AI stuff here, some of it at least. I graduated from UMass a couple years ago. I'm working as a technology consultant now, so I work with businesses that are both building technology platforms that they're integrating AI with, as well as existing companies that are integrating AI. And then I also do some stuff outside of AI that's more software engineering and product development focused. I think that's all you need to know about me. I am happy to give this email to anybody on a piece of paper. If you want to reach out to me, talk more about any of this stuff, totally happy to talk to anybody at any point about it. So, Paul already mentioned we are doing some seminars on these things that are non-technical. They're talking more about AI tools, things that are out there, how to use them, general public education type topics. We're also going to be doing some workshops, which is what we're here today for. These workshops are a bit more technical. Some of them are a lot more technical. And today's focus is going to be on neural networks. So we're going to start off just kind of framing what neural networks are. I'm going to explain at a pretty high level how they work, talk a little bit about the math and mechanics behind them. Not really in depth, though. It's going to stay pretty high level. And then we're going to go through some code. You guys are all set up to code along or just to follow along with it. I'm going to go through things and just try to pick up what you can, absorb as much information as you're able to. And I think it'll give some good background, a good taste of it. That's really what this is about. This type of stuff would often be taught over an entire semester of 3 times a week, hour-long class sessions in an undergraduate setting. And typically you would need prerequisites of like linear algebra and calculus 2 before you would even be taking it. So just to give an idea of why it's difficult to cover in the amount of time we have. So starting out kind of broadly, AI itself, what is it? It's both a field and also a noun that means intelligent systems, basically. So when we use the word artificial intelligence, we're talking about systems that do things in a way that appears intelligent to us as humans. We're also talking about a field of computer science. A lot of people who aren't familiar with it don't realize this, but AI as a field has been around since the 50s. It was usually attributed to Alan Turing as the person who kind of started the field. And the idea of neural networks has been around since the 50s as well. AI is a huge field, like I was saying. There's a ton of different things that are kind of wrapped up in the field of AI. It pulls from many different fields. I mentioned mathematics. That's really the basis for most of AI as a field. And nowadays, there's a lot of pull from fields like neuroscience and psychology as well. These are kind of a random sampling of aspects of AI as a field. And neural nets play into a lot of these different things. Specifically today, we're actually going to be talking a bit about computer vision. So the example code we're going to go through later is under the umbrella of computer vision, and that's basically using AI or at times non-AI stuff to analyze visual data. So images typically, it also applies to videos. There's a lot of stuff that's going to be very hand-wavy because I am not going to be explaining the math behind it because it would take far too long and just completely get people lost. But I'm going to try to explain a general idea of how most neural networks work, like the general idea of them. So when we're talking about neural networks, the reason they're called neural networks is because they come from ideas about the human brain. And the human brain is made up of a bunch of neurons, which are a particular type of cells. They're all connected in this big network. Really the network, talking about the bio side of things, is more than just your brain. It is connecting your entire central nervous system. And all of those neurons pass messages between themselves, essentially. And we start off with these things that people call neurons. They also get called nodes sometimes, and they're organized into layers. So the example that we're going to be loosely talking about, and the one I'm going to draw here is different than the one we'll see in the code later. The one in the code would be way too big to try to draw it. This is just like an overview idea of it. What we have are 3 layers of neurons, and the way that neural networks work is you pass data into them, and it flows through layer by layer and has some kind of processing done to it. That's like the very high level idea. So in our case, what we're doing is we're going to be putting images into the first layer of our network. So this is called our input layer. When I say images, to people you're thinking of maybe a picture of a landscape and you can look at it and there's a bunch of color and it looks pretty. To the computer, the way images are actually stored, there are big matrices, and you're going to hear me using that term a lot. If you're not familiar with it, and I know some of you probably don't have the math where you would have really seen or heard what that is or maybe remember it, it's basically just a big grid of numbers. So you'll have, just pretend these are all numbers. You'll have like x1, x2, x3, et cetera, et cetera, et cetera. And they'll go off in two directions, the way I'm showing you now, and you'll just have like a grid where every one of these circles is a number. And this is how images are represented in a computer, where each number is a particular pixel in the image. So neural networks fall under this category mathematically of what we call a universal function approximator. And basically what that means is that it learns a math function. So you've probably all seen like f of x, and then you put something in for x, and it might be like something very simple. You put in x, then you can calculate what f of x is. What neural nets are doing is they're guessing at a particular function. And they're a lot more complex than something like this, but that's the general idea. Each of these neurons gets a number. And it's one of the numbers in the image, one of those pixel values. And then it will pass it to the next layer. And there's a lot of different ways you can build these things. And there's a ton of research, like I was saying, it's been going on for years about different ways to build neural networks. And sometimes we connect every neuron in one layer to every neuron in the next layer. Sometimes we don't. Sometimes it's better to, sometimes it's worse for particular tasks. And sometimes in the research they understand why it's worse, and sometimes they have no idea, but they can just see that it doesn't work as well. And there's a lot of stuff like that in neural networks where, because it's all math, there's tons of these numbers. We call them hyperparameters. They're basically settings about how you do particular math or how you connect things, how you build the network. And a lot of the research around neural networks is about discovering and optimizing these hyperparameters. So it's about finding the values and the settings that work well for a particular task. So information flows through. We call this a hidden layer because it's not an input or an output. It's just the network passing stuff through this layer inside of it. And this is really where the magic happens in neural nets. So each neuron here can do something. It can do some kind of math. And each one of them has another one of those matrices, like we were talking about, associated with it. And we call those weights. And those are really the magic thing in neural nets in a lot of ways. But basically, each one of these has another big matrix, huge, like incomprehensibly large in most cases, of numbers. And they're usually pretty small values, a lot of different approaches to it, but it has some set of numbers in it. And these are not something that we set ahead of time. These are called learned weights. So this is the information that the neural network actually learns, which is pretty different than how it works in the human brain, but it has parallels to it. In reality, this is what neural nets are doing, no matter what problem you're solving, except it is doing it with a number of dimensions. So we have two axes here, an x and a y, and then you can kind of, in your head, picture like if we had a third axis, like a three-dimensional graph, you could put another axis going this way and have like these points floating. But neural nets deal with things that are often in hundreds of dimensions, so they're stuff that humans can't really, we don't have a way of visualizing that. So you could have, like 100 data points here, like all these different things about a person, and maybe they correspond in some way to whether or not that person's more likely to like apples or bananas, and we can't really picture how all of that data possibly turns into something like this, but that's essentially what the neural networks are doing. They're doing this in very high-dimensional space, and with all that math and a bunch of like matrix multiplication, they're learning some function in like huge number of dimensions that's able to divide the data and guess based off of where that data lies. When we are training the neural network, we're trying to get it to learn that function. And this is probably, this next bit is going to be the most hand-wavy and difficult to follow. So if you can pick up the gist of it, you're in a good place. To predict something, we put data in, and we get to the end, and then each neuron at the very end is going to have a number in it, just one number in every single one of them. And that number could be low or it could be high. but one of them is going to have the highest number. And that one that has the highest number corresponds to what the neural net is guessing the class or the label should be. So if we put an image in and we tell it, we train it ahead of time, and then we want it to predict something, we give it an image and we say, in this case, maybe we have 3 output neurons. One's for ship, one's for truck, and one's for dog. And we put an image of a dog in. We want the dog neuron to have the biggest number in it at the end. And if we did that, then we did a good job, and the neural network got it right. If it put a bigger number in the ship neuron, then it's saying, I am more confident this is a ship than a dog, in which case it's wrong. And so for training, we basically take a huge amount of data, we split it up into tiny batches, and then we feed in a batch at a time. And we let it predict, and we get, at the end, its best guess about what that image is. With this data, we know what the correct answer is. So we use something called a loss function. Essentially what the loss function does is it takes all of the numbers at the end of a guess, and it tells you how good of a job the neural net did about guessing the thing. How close was it to getting the right answer? And that comes down to mostly probability and statistics. And so that's kind of what those functions are made with, built out of. And so we haven't actually done anything. It hasn't learned anything. It's just guessed something, and we've looked at how close it was to guessing it correctly. Now we have to actually teach it somehow. And we do that using some things that, if you know calculus, are pretty intuitive. If you don't, might be confusing, but I think I can explain them in a somewhat non-confusing way. Before I explain it on the neural net, I do need to explain very vaguely what a derivative is. A very simple way of thinking about it, in the way that we need here, is that a derivative is how a function is changing at a particular point. That's the only way we're going to think about it today. So if I pick a place, so this is some math function, I pick a spot on it, and I want to know what the derivative is here. I want to know how is the function changing at this specific point. So if I'm here, and then I go just slightly to the side of that, how has it changed? And in this case, we're going up a curve, we're going up a slope, so the derivative would be positive. And so we know that if we step slightly to the right, we're going up. And if we step slightly to the left, we're going down. We have a negative derivative. And in neural nets, this idea of derivatives, we usually call them gradients, not derivatives, and it's because essentially we're dealing with a huge number of dimensions. So we just call it something different. But the idea is pretty much the same. Now, I know that just seems like a random fact I just gave you, but we can use that as the basis for training neural nets, essentially. Because at the end, we had this loss function we were talking about, where it's a function that tells you how close you were to getting it right. And if we can get derivatives that tell you if you move just to the right or just to the left, if you're going to go up or down on a function, that's pretty much the basis of training in neural nets. And that's pretty much it on a very high conceptual level. That's how they learn. And it comes down to just a huge amount of data being fed through them. And so, like, in review, I know this really got out in the weeds, but in review, basically, to train a neural net, you're putting something in our case, an image, and then you're putting it through layers where we're doing math to it. So we're multiplying it by a bunch of numbers we've learned over time, or at this point haven't really learned yet. They're kind of right, but not quite there. And at the end, we say, how close were we? We go back, and we call this back propagation. We go back through them, and we nudge all of the numbers that we're trying to learn a little bit closer to what would have given us the right answer, just a tiny bit. And then we do that for this data set that I'm talking about, 50,000 images in the training set, and we do 50,000 times some number of things we call epochs. It's basically how many times we go through the entire data set. So in our case, we might do it for 50,000 images and then do 100 runs of that. And so you can see how this is like a huge number of times that we're doing this and nudging the numbers, nudging the numbers, nudging the numbers. And if you have good data underlying it that actually correlates to the class, which an image does, right? If we have an image of a ship, if you look at it and it looks like a ship, it's probably a ship. So that's good data correlation. And if you do that a ton of times, eventually you get a network where you'll put something through and it'll have a pretty good chance of coming out with the right guess. So we're going to talk now, and this is kind of the last thing I'm going to try to explain before we just look at some code. We're going to talk about something called a convolutional neural network. Really what we're going to talk about is how a convolution works. A convolutional layer is basically where we take one of those neurons and we make its matrix like a very particular size, and then we just call it a kernel, another math term that we're stealing for AI stuff. And a kernel is just another one of those matrices. This one I'm going to draw slightly differently. It's the same thing. It just makes more sense to draw it in a grid. And I'm going to go ahead and put a grid kind of over here as well. It's going to get more and more messy as I go. We'll just pretend this is like a nice grid, and each square has a number in it. This is our kernel. These are the numbers that have been learned inside of our neuron. And a convolution is basically, we tell the neuron that the math it should do is it should take the numbers that it's learned, and it should take its kernel and use it like almost like a viewfinder or a filter. Viewfinder is probably the wrong word there. Do you know when you look at like a solar eclipse and you take like the little pinhole so you don't see too much light? That's kind of what we're doing here. We're basically like clamping what it can see at any one time and having it just do math over a particular area. And then it will take those numbers and do something here. Usually it's multiplying all of them and then adding it all up to get one new value, or it's multiplying them, taking a max or something. And it'll calculate a value from the ones it can see. And then it'll slide the kernel over by one, do it again, slide the kernel over by one, do it again. And it'll do that until it's covered the whole image. And what you get is another matrix of numbers, because that's all neural nets are. The neural networks are approximating functions. And I think you led right into the last point I want to make, which is awesome. What's really interesting about it is that we're not telling them exactly how to look at it and to understand it. We're not really giving them any instructions. And a lot of other typically older artificial intelligence approaches, like traditional machine learning, you kind of coach it a lot more. You tell it like, these are the specific things you should look at. Like you might build by hand an edge detection algorithm and be feeding the output of that into your machine learning system with different approaches, older approaches. Neural networks don't require any of that. And there's ways that you can use those techniques, but what's really, really cool about them is that fact. That's like the really neat thing about them, is that you're just giving them data at the end of the day. With these weird in-between layers, I think it's very possible that some of you have actually seen stuff like this before. If you're around STEM things, you might have seen some stuff Google was doing. They called it Deep Dream, I think. Really weird images. This was before modern day like generative art stuff, where they would take an existing image, or I think they had a version of it that didn't even use an existing image, and they would make it look like very strange to us as humans, stuff like this. So you take a picture of a dog, and then this is sort of what it was known for doing, was it kind of found, like, I don't know if you guys can see it super well, but it finds like little faces and makes faces where there aren't any, because it was trained on a bunch of face data, I think, something like that. It's been a while since I've looked at it, but it's just an idea of how weird representations in neural networks can be, but these are outputs of a kernel doing convolutions over an image. I'm not sure what the original image is. These are from a research paper, and I think that they just kind of set up a random example for this. But the pictures would be something like, you can see here, this is clearly like an eye of something. And then in the convolutions, you can see it recognizing things that to us like coarse. So, Colab. I'm guessing none of you have heard of a Jupyter notebook before, but that's what this is. It's this thing called a Jupyter notebook, and they got made up a little while ago. They're really useful for people doing like research that involves code. You can put blocks of text and blocks of code next to each other in the same document, and then you can run that code without taking it out of the document. Okay, on your notebook, up here in this bar, right under where your username and settings are, there's a little drop-down arrow right there. It's next to the green graph-looking things. You're going to click that. You're going to click Change Runtime Type. Should be the second option down. You should have three things you can select. You want to select the one that says T4 GPU. Select that, and then just click Save. Now you'll be able to run our code on a GPU somewhere. So neural networks, machine learning stuff, AI generally, uses GPUs. often rather than CPUs because it's a lot faster. We're not going to talk about why. It's complicated. It's because of matrix math, basically. They can do stuff way faster if you run it on a GPU. And when you're talking about 50,000 pieces of data running over and over again, that's usually considered a very small data set, and even that is massive, so we want to be using that if we can. This first block is not code that actually matters. This is a bunch of library imports, we call them. If you know programming stuff, you know what I'm talking about. Basically, to build this neural network, we are not doing it from scratch. If we were doing it from scratch, we would have to write essentially our whole own library of all of the math that makes neural networks work, and that is, 1, very time-consuming, 2, very hard. So we're going to be looking at 3 different main pieces of code. The first one is going to be actually building our neural network, so defining it. The next one is going to be our training loop, it's called, which is where we go through putting data through it, adjusting the numbers, putting data through it, adjusting the numbers a bunch of times. And then we're going to have something called test loop at the end, which is where we give it new data that it hasn't seen before, and we just look at how good it did, and how good of a job, and then we can basically get like a % correct off of that. This is like the meat of the code. This is us defining a model or a neural network. When you're using PyTorch, which is the language that we're using, or sorry, the framework that we're using, you define a neural network as a class that inherits from this thing that they give you. So what that means is basically they have like a framework for what a network looks like, and when you want to make a new network, you make another framework, and you take everything from their framework, you put it in yours, and then you add stuff to it. And so this is kind of like neural nets and also programming 101 and like a bunch of different things going on. And then in here, we're going to define really one important thing, and that's this function called forward. And what that function called forward is instructions to do the thing I was explaining, where we put something in and then get the buckets out at the end. That's what that forward pass is. That's us defining, here is how you do the forward pass. So you can think of it as like passing something forward all the way through the network. And this is about the level that most, a lot at least, of neural network research is done at, actually. It's very unusual as an academic that you would be manually implementing a new framework to do this stuff. So this isn't, the stuff that we're going over is actual code that would be used in settings where you're studying neural networks and things, or sometimes using them in production instances at a company or something. Because the framework's really good. It does that math really efficiently. It's super optimized, and so it doesn't make sense for people to constantly rewrite it. OK. So that's an idea of what we're coding here. It's really this function called forward. We're going to go through it and explain what everything there's doing. The other piece of this is up here. So this is in a function called init, which stands for initialization. If you know Python and you know object-oriented programming, you probably know what this is. If you don't, that's fine. What you do need to know is that we are basically just customizing a few layers in here. So we're making our own versions of a few specific types of neuron layers. So the first 2 are our convolutional layers. So those are the ones that pass that kernel thing over the picture. And we're basically just going to set up a couple custom ones. And what you're seeing here is nn.conv2d. Basically, this is saying create a new PyTorch convolutional layer. We want it to be 2-dimensional. And then the parameters that we're giving it, for, again, I know we have various different levels of programming experience here. We're passing it numbers, so we're giving it some particular configuration numbers. And these are kind of hyperparameters, kind of not. Like, they're kind of a little more basic than that. These are basically describing, we call it the shape of the data that's coming in, and then the shape of the data that's going out. So I was talking about how the matrices are like different sizes at different points and stuff. And as you do this math, you're constantly changing what the matrix looks like, how many like numbers across and down it is, so the dimensions of it. We're also changing what we call the channels, which I mentioned this earlier, but like you have a different matrix for the red, the green, and the blue in an image. When you pass it over, through a layer, you can have that layer create new dimensions that didn't exist before. And these are all generally arbitrary, except for the ones that are by requirement. So what I mean by that is when we first feed the image in, it has 3 channels. So like we can't put a different number here. And I know this is like very arbitrary about knowing the framework. I have links to all that if you guys want to read the documentation. But basically, we have to tell it things like that. We have to tell it, you're getting 3 channels. We want you to be outputting 16 channels. And then we're making the kernel be a 4x4 grid. That's what this is saying. And then the next one is very similar. It's another convolutional layer. So we're telling it, you're getting 16 channels, because that's what the one before it will produce. We're going to have you output 32. And again, the 32 and the 16 here are just numbers that work. It's kind of experimental. You can play around with them. That's hyperparameter tuning. And then, again, we're going to do like a 4x4 kernel. And the kernel sizes are the same way. They're very arbitrary. It's an open problem, what works the best, and it totally depends on the specific data set you're using. The last 3 we're defining are more simple in how they work than the convolutional one. This is something I didn't talk about earlier. It's called a max pool 2D. Basically, it's like a kernel. We slide a box over whatever matrix is there, but instead of doing any more complex math, we just take whatever maximum number out of the 4 or 5 that we're looking at is the biggest, and that's what it spits out. And then our last 2 are what we call linear layers or fully connected layers. You'll see that later in the code. Those are ones that are just like the original example I gave, where you're just putting it through, it multiplies it by all the numbers it knows, and then it spits something else out. So they're kind of like the most simple, like classic type of layer. And this is the part where this is going to be different than that, because we're putting more layers in our example in the code than I was showing on the board. Essentially, we're going to have layers that are kind of split up into blocks. I tried to separate them out somewhat. There's a little bit more nuance in here, and you guys will probably see some things you don't recognize, like this ReLU thing. I didn't explain that. It's a pretty important part of neural networks, but without getting into the math, it doesn't really make sense why it's so important. They're what we call an activation function. So they're basically one extra step that we do after we do a convolution. We basically put the numbers through this one other function that we have predefined. And there's a lot of different functions that are used for that in practice. They do 2 important things. One, they make sure that the numbers stay within like a certain bound usually, so that we don't get numbers that go way off in one direction or another. And 2, they add what we call non-linearity, and that's getting into math that I'm not going to explain fully right now. It is very important. Without that, the network doesn't really do anything interesting. It's a really important piece on the math side. And then this pooling thing is what I just talked about, where we're taking like the max value and kind of shrinking it back down a little bit. So altogether, those 3 things make up what we do in one convolutional layer. So it's actually 3 different steps, but you can think of them as being like one process within our network, one of those layers. So that's our first convolutional layer. This block of lines 16 through 18 is the next convolutional layer. It's basically the same here, except with different dimensions, because we've changed what that matrix of numbers looks like. Then we do something that I also didn't talk about, but this is super simple, and I actually mean it this time. We flatten it, which basically means we take that matrix that has a bunch of different dimensions. In this case, it's actually just technically 3 dimensions because we have those channels, but we're thinking about it in 2 dimensions. So this is a pretty good example to use. Flattening it, we just take it from being 2 dimensions, technically 3, we make it 1. So we just take all the numbers and we take like, this isn't exactly how it's done in the framework, but the way you can think about it is just like row by row, and we just take one row, put it in a line, take the next row, put it in a line next to it. And what you get is just a really long sequence of numbers instead of a big grid. So we flatten it, and the reason we do that is, again, it's kind of hand-wavy. It just works well for this particular type of problem to do that to them before we start passing them out to the output. There's a lot of reasons in practice that you might flatten them. You might want to have a layer that does some math that only works in 1 dimension. You might want to add some kind of sequencing to it. There's a lot of different reasons. In our case, we just smush it down to make it easier to work with, kind of, is how I would say to think about it. It obviously does change some of the math, but that's fine for now. You don't really need to think about it. So we squish it down, and then we hand it to our 2 layers, which up here we were calling linear. And those are the ones where it just looks like this. It's just multiplying it by a bunch of numbers and passing it along. And the reason we have 2 is because one of them is doing something like this, multiplying by a bunch of numbers and handing it off. The next one is doing something like this, where it's not outputting it anywhere. And so you'll see that when we defined that last fully connected layer, we said new linear layer, which just means like 1-to-1, just a bunch of neurons that are doing the same thing. We give it an output of 10. And the reason that there's 10 is because each one of them, like we said, is basically a bucket. And so at the end, all will come down to our last layer, and now X will be a set of 10 numbers, and each one of those numbers is a bucket, and it'll be really big number in that bucket if the network thinks that it's that thing that that bucket is labeled as. It'll be a very small number if the network's very confident that it's not that thing. This is the thing that I'm just basically going to completely hand wave over. This block is us downloading our data. There's not too much value in me explaining most of this. I'll mention a few things, but generally if you're working with networks, we'll be getting data from somewhere, and it'll be different depending on what data set you're working with. So explaining this in depth is not super conceptually valuable. Basically, this whole thing is grabbing our data, and we're loading it all into a format that we can use it in here. So we're taking a bunch of images, we're like adjusting all the numbers in the pixel grids to be like within the ranges we need. We're reorganizing it slightly and putting it into different data structures that Torch uses and can do math with really quickly. That's pretty much the extent of it. If you're curious about it, or if you've worked with like ML libraries before, we are grabbing a data set that PyTorch offers in like a nice data format already, which is why there is not more processing here. They're already in a very clean format. The only interesting thing that I will point out are these 3 sets here. Well, really 2 sets and then 1 line. This is what we call the train test split. So I've mentioned that we have some data that we use for training, and then we kind of keep a little bit of it off to the side, and we don't let the network see it, and we just save it so that at the end we can test and see how well it did. If we trained on everything, including the stuff that later we're going to use to evaluate the network, it can end up doing something we call overfitting, and you wouldn't know it, which is where it learns really, really well how to predict, but only on those specific pictures you gave it, which isn't what we want. If we want to be able to later hand it a different 32 by 32 picture of a ship, I don't know why you'd want to do that, but if you have one of those and you want it to be able to recognize it's a ship, you have to know that it didn't overfit, we call it, to the data. So that's why there's 2 different data sets in here if you're looking at the code later. And then the third thing is just our set of classes. So if you have the code up, if you're wondering what else is in there, frogs, horses, trucks, lots of other important things. Finally, down at the bottom, this is, I'm not really going to talk about it, but this is just some code to show a batch of images. So you can run that. If you run it, and after it finishes doing its downloading thing and everything, you don't see pictures, let me know, because something's wrong. I can potentially fix it or tell you how to later. You should see like a grid like this. If you want it to be a little more clear what label goes with which thing, you can adjust the batch size at the top to be like 2, and then it'll show you 2 images. If you do that, you'll probably want to come back later and make the batch size a bit bigger before we train. So just keep that in your head. If you change that number, that's fine. You'll just want to adjust it later if you're going to try to train this in the notebook. But this is just a set of the pictures from there. It's kind of funny. It's actually a lot easier to tell what they are when they're really tiny up on the projector. If you have them in front of you on your laptop and you look at one and it's like this big, I don't even know how the neural network learns it. I can't tell what they are half the time. But this list of stuff it spits out is like item by item what it's labeled as. So that's a truck, a plane apparently, a cat. Like I said, some of them I can't even tell what they are.